So again, if you guys are still having trouble with pointers, that's perfectly normal. That's perfectly okay. Normally it would be a topic we'd spend like 2 weeks on if we were just dedicating a class to C. So if you're still a little bit lost, that's fine. Just make sure that you stop by office hours to get help and work out what's going on. The other thing is we're actually going to start on the real lecture material, so hopefully we'll get you enough to know how to do your homework assignments. Yeah?
Where's our quiz?
Your quiz will end up appearing once we've covered enough material for you to be able to do it. The TAs were working on translating the questions to appear on Mimir. They've mostly done it, but it might be another couple more days before it shows up. Yeah. So, like, the homework one is probably going to be moved back at least 2 weeks, I think. Probably has to be like week and a half to 2 weeks before it'll be due, because we just haven't covered the material yet. Yeah.
Does it also affect the rest of the homework?
Yeah, I mean, all the homeworks are going to have to be delayed because it's taking us longer to get to the material. Yeah.
But the due date on the Mimir did not change.
Yeah, I know I haven't changed the due date on Mimir, but I promise you, it'll change. You will have sufficient time to complete the assignment. Don't worry about it. Okay, so right now, this is the big takeaway that I want you to get from this class, or at least one of the big ones, is that everything inside your computer is represented with bits. There's absolutely no exception to this. So your integers, your shorts, your doubles, your floats, all ints. Your text files, your video games, your music, your videos, everything inside your computer, it's all represented using bits. A bit is simply shorthand notation for binary digit. And binary digit, since it's base 2, just binary means 2, can either have the value 0 or 1. A group of 8 bits is called a byte. And a group of 4 bits is called a nibble, because a nibble is a small byte. Right? Someone's been really cute when they're coming up with the naming convention there. Right? So since everything is represented with bits, and that's all that we have to work with inside the computer, we have to figure out how are we going to represent our ideas inside the computer with bits. So we have to come up with some mapping from our high-level ideas to some bit string representation. And every unique idea that you have has to have a unique pattern to represent it, at least in some unique context. So if you have S unique states you want to represent, you need the ceiling of log 2 of S bits. And if you have B bits, you can represent 2 to the B unique things. So to give you an idea of this, let's say we have old MacDonald and he has a farm. And on the farm he has a pig, a duck, a cow, a chicken, a dog, and a cat, right? Pig, duck, cow, chicken, dog, cat. That's 6 things. So if we apply our formula from previously to figure out how many bits we need to represent each of our animals, we would do log 2 of 6, which is going to be 2.53. Take the ceiling of that, right, which means always go up to the next integer above this value if you're below an integer value. And so we're going to get 3. So you would need 3 bits to be able to represent the animals on old MacDonald's farm. And so we have to come up with some mapping to how we might want to represent each animal, actually assign that bit pattern. So over here we might say 000 means pig, 001 means duck, 010 is a cow, 011 is a chicken, 100 is a dog, and 101 is a cat, right? We're going to have 8 possible representations though, so 2 of them aren't going to end up being used. Any questions so far? Yeah.
So why are we using 8 instead of 6?
So we're using, so over here we have 6 states, so like 6 unique things, right? Which requires 3 bits. With 3 bits though, you're going to have 2 to the 3 unique things that you can represent, 8. So if we only had 4 bits, we wouldn't be able to represent enough information, right? 2 bits, we'd only be able to represent 4 things. And so we wouldn't be able to represent each one uniquely, right? But with 6 bits, we can represent, or with 3 bits, we can represent 8 things. but we only need to represent 6, so 2 of the patterns end up going unused. Does this make sense so far?
Can you go over that formula again?
If you have S unique states, you need the ceiling of log 2 of S bits. Like, how is that derived?
Yeah.
It's kind of derived from the inverse of the bottom function to the B, right? If you have 1 bit, 0 or 1, how many bits how many unique things could you represent?
Oh, I understand.
2, right? If you had 2 bits, you could represent 4 things. 3 bits, you could represent 8 things. 4 bits, 16. 5 bits, 32, right? So if we want to do the inverse and go back, right? The inverse of exponentiation is logarithms. So log 2 to go backwards. Any other questions? So over here we have another mapping, right? So we said that 0, 0 has no meaning. 0, 0, 1 is chicken. 0, 1, 0 is a cow. 0, 1, 1 is a duck. 1, 0, 0 is a dog. 1, 0, 1 has no meaning. And pig and cat are down there at the bottom. Which of these mappings is better? Mapping number 1 or mapping number 2? Mapping number 1? Mapping number 2? For those of you that say mapping number 1 is better, why do you say it's better? Okay, so it's continuous. And how does that help you? But this isn't in an array, right? These are just the bit patterns that we're going to be using to represent the objects, right? So yes, if we had some sequence of like pigs, right, we'd have 0, 0, 0, 0, 0, 0, 0, 0, 0, right? To have 3 pigs, right? But if we had like over here, we want to do 3 pigs, 1, 1, 0, 1, 1, 0, 1, 1, 0, 3 pigs. Is one of those better than the other one?
I would say the first one is because the 2 highest ones have no meaning. So you're not going to, the moment you get to one with no meaning, you can stop.
Well, again, if we have these elements that have no meaning in our program, should those ever show up in our program if our program's written correctly? No, right? So it shouldn't really matter. This is kind of the idea of like, what we're doing right here is basically doing enums, if you guys have worked with those before. But I would say there's really no one that's better than the other. They're both kind of equally valid in this case. But when we go to pick mappings, the mappings that we pick, they are completely arbitrary. They're whatever we kind of feel like at the moment. But when we do pick mappings, we want to kind of choose ones that are going to work well with our hardware and maybe work well if we have to do some other work well in our program. So we generally try to pick mappings that have regular patterns to them, as well as ones that are easy to represent in the hardware if we have to implement that stuff inside the hardware. Sometimes we'll have patterns that don't map to anything. Super normal. Again, if we have these patterns, they probably shouldn't show up in our program at all because they have no meaning in our problem. If they are showing up, it means you screwed up. And you should go fix that. Any questions so far? So, let's say we wanted to do a problem. Let's say we wanted to figure out how many bits we need to represent a special clock. Let's say our clock only has hours on it, right? So the hours 1 through 12. But we can tell time to the nearest quarter hour. Also, there's a window in our building, so we can look outside to see whether it's night or day. How many bits would we need to represent this particular situation? All right, let's pop that up somewhere so we can write that down. Here. No, here. You have a clock with only the hours on it. but you can tell time to the nearest quarter hour. You can also see outside to tell whether it is light or not. How many bits do you need to represent this situation? So to figure this problem out, what do we need to, before we can figure out how many bits we need, what do we need to know first? How many states? So how many states are there? Well, how many hours are on the clock? 12, so there's at least 12 hours, right? But for each of those hours, we can tell time to the nearest quarter hour. So how many hours are there, or how many quarter hours are there per hour? 4, right? So that's 12 times 4 possibilities, right? We have 1 o'clock, 1:15, 1:30, 1:45, and 2 o'clock. So 4 per quarter hour, right? Times the day or night, AM or PM. 2. So this is going to give you 12 times 4 times 2, which is 96, right? So now you would need to do log 2 of 96, which if we open up idle and say from math import log, right, log of 96 base 2 is 6.58, and so we have to take the ceiling of that, which is going to be 7 bits. Yeah?
Why would you multiply the number of the different states instead of adding them?
Because there's a lot of different possibilities, right? For example, let's say you could have a car that could appear in 3 different colors, right? And 4 different sizes. How many different types of cars are there? Is it 3 plus 4, 7? No, it's 3 times 4, which would give you 12 unique cars, right? And so in this example, we had cars that could have 3 colors and 4 different sizes, right? How many bits would we need to represent this car? Or be able to represent a car uniquely? Like log 2 of 12, which is going to, then you take the ceiling of that, so you actually would need 4 bits to make that happen. Any questions? What happens if we try using fewer bits than what we have, or than what we need, right? So in our example, we said that we needed 3 bits to do the problem at old MacDonald's farm. What happens if we only had 4 bits? Insert table. Right, so here's your bits, here's your animals. So over here, right, we have 0, 0, 0, 1, 1, 0, 1, 1. And then again, we have dog, cat, pig, chicken. What else do we have? Duck and a cow. Right? So we have to put duck and cow somewhere. So maybe we put duck here and we put cow here. So if we see 0, 0 in the 0, 0 pattern in our program, what does that mean? You can tell whether it's light or not. You can also see whether it's light or not. Is it light outside? Is it AM or PM?
So, but on a regular clock at 12 p.m. and 12 a.m., you make representations.
Yeah, well, it shows up on the same, but that clock might say 12 a.m. or 12 p.m. But when you look at that clock, right, if you look at it and you're like, oh, it's 12, and you look outside, right, and you see that it's light outside, is it 12 a.m. or 12 p.m.? 12 p.m., right? So you know that it's different than 12 a.m. when it was dark outside. So that's a different state. Because again, it wasn't say necessarily to represent the clock, it said to represent the situation.
Okay, I didn't know if it meant that information rotating, we could just tell by looking outside. So if we had the bit and it was the same, we'd be able to tell AM or PM by just looking at it.
Yeah, we can tell it's looking outside, but we want to see like how many bits do we need to encode each of these situations. So if we saw 0, 0 here, what would that mean? If we saw some animal in this example that was encoded as 0, 0, what would that mean? Is it a dog and a cow? So this animal is both a dog and cow? Or would it mean it's a dog or a cow? So it's both a dog and a cow. It's either a dog or a cow. It's going to be the or situation, right? Because if you come by your dog, you're like, dog, I give you this bit pattern 0, 0. You go up to the cow and you're like, bit pattern 0, 0. You go up to the next cow, 0, 0. You go up to the next dog, 0, 0, right? And then, but when you go back through and you read it, you're like, well, this thing's a 0, 0, but that's what I'm labeling as I'm labeling either dogs or cows as 0, 0. So I couldn't tell which one it was. It's either one of these two things. And that's what happens if you don't have enough bits. It's either this or that, but I can't tell you which one it is specifically. So let's talk about variable sizes in 32-bit C. An integer is going to be 4 bytes big. A short is 2 bytes big. A character is 1 byte big. A float is 4 bytes big. And a double is 8 bytes big. Don't ever use these hard-coded constants in your program. Always use size of when you're working with these things so that your program will be like cross-platform compatible without you having to make any changes. Because if you go and you compile that program on a 64-bit machine, it might actually have integers as 8 bytes big. But you don't have to rewrite your code because you use size of, and then the compiler took care of the fact of what the size of that thing was. But we'll use these numbers here in examples kind of going forward. So let's talk about some of the operations that you can do with bits. The common bitwise operators are AND, OR, NOT, XOR, left shift, arithmetic right shift, and logical right shift. So when we're working with bit patterns, we're going to say 1 represents true and 0 represents false. So not A is tilde A. It's the opposite of A. It essentially means flip the bits of A. Everywhere you had a 0, you're now going to have a 1. Everywhere you had a 1, you're now going to have a 0. A and B is only true if both A and B are true. So you need a 1 in both spots for them to be true. A or B is true if either A is true or B is true, or if both of them are true, and A XOR B is true if exactly one of them is true. The operations are really similar to their logical equivalents, but the operations are performed on bits, and they're not performed on single elements, like logical values, like logical and logical OR. So again, you guys have probably seen this truth table before many times, describing how NOT, AND, OR, and XOR work. And again, they're just the definitions from previously. So here, not A, everywhere A had a 0, not A is 1. Everywhere A was 1, not A is 0. A and B is only true if they're both true. So both false, one of them's false, one of them's false. Oh, they're both true. So true here, false for the rest. A or B is true if either A or B is true. A or B is both false here, so false. B is true, A is true, both true. So true, true, true. And then A XOR B is only true if exactly one of them is true. So 0 or 1, exactly 1 true. 1 or 0, exactly 1 true. Both true, false. No trues, false. You guys have all seen this before, right? Hopefully. So here's some examples of doing some bitwise operators. Here's A, it's 1100, and here's B, it's 1010. So over here, if we do not A, everywhere you had an A, you now have, or everywhere you had a 1, you now have a 0. Everywhere you had a 0, you now had a 1. The bits get flipped. A and B, notice it's being done on each spot. So true and true is true. True, false, 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 true, false, and then false, false, false. So again, it's doing the ANDing and the ORing and the XORing all on the bit level, not in terms of like a logical constant, like this thing is true and this thing is false. It's working on each of the individual bits. Any questions here? So let's talk about shifting. Shifting moves all the bits in the specified direction. So if you left shift A by n, all the bits move n to the left. Any bits that were on the far left, they get pushed out and thrown away, and so they don't have spots to fit anymore. And then zeros are brought in to refill in the missing bits. This can be interpreted as multiplying a by 2 to the n, but it does not always mean you are multiplying a by 2 to the n. Sometimes use it as a shortcut. Sometimes you really just mean I want to move the bits over. The reason why this can be interpreted as a times 2 to the n is if you think back to base 10, if you multiply a base 10 number by 10 to the n, what do? So if I multiply a number by 100, what do? You add 2 zeros. If you multiply a number by 1,000, add 3 zeros. But here, since we're in base 2 with our numbers, when you move them to the left and you add zeros, you multiply by 2 to the n instead of 10 to the n. There is a logical right shift, is you move the bits from A to the right by n. Again, bits that can't fit in get discarded, and zeros are brought to fill in the missing bits. And then the arithmetic right shift also moves the bits to the right by n. Bits that can't fit are discarded, but instead of bringing in zeros every single time, you bring in the most significant bit. So if the most significant bit was zeros, all the bits that you have to fill in get filled in with zeros. If you have to fill, if the most significant bit was 1, the bits that you would fill in would be 1s instead. Notice here that logical right shift and arithmetic right shift, they're written identically, right? There's no difference between how you write them. But how are you going to specify whether you want a logical right shift versus an arithmetic right shift, right? Because how do I say which one I want? The right shift, which one ends up being done, depends on the type of the variable. So if the thing that we're trying to shift is an unsigned variable, like an unsigned int or an unsigned short or unsigned char, it will do a logical right shift and you'll bring in zeros. But if the thing that you're working with is a signed variable, like int, char, or short, if you right shift it, you will do an arithmetic right shift. Does that make sense? So the type of shifting that you do is going to be based on the type of the variable. If you right shift an int, you'll do an arithmetic right shift. If you right shift an unsigned int, you'll do a logical right shift. So be careful with that you do the one that you intend to be doing. So here's some examples. So let's say we want to shift A to the right by 3. So all of our bits move to the right by 3. So you can see that this one moved 1, 2, 3. Good. He moved 1, 2, 3. So we should have a 1 there. Oh no, we're going to the left. So everybody moves to the left by 3, right? So we're going to, since there's no space to fit these 3 bits, they get discarded, because if you move them to the left by 3, where are they going to go? Well, they don't have anywhere to go, so they get thrown away. So our new most significant bit is going to become this bit right here. So we're going to have 1, 0, 0, 0, 1, but we're going to have 3 blank spots left over. So then we bring in 3 zeros to fill in that spot. Or if we take things and shift them to the right by, or to shift them to the left by 4, right? There's no space for any of these bits, right? So we're left with these bits up front, 0, 0, 1, and then we bring in 4 zeros to fill in the blank spots. Any questions on the left shift so far? Does anybody want to see a more detailed example? The bits moving over? Okay, it's just really hard to type it out. So let's say that down here, right, here's our bits. Let's make a table. So let's say that we want to left shift by 3, right? If we take this bit right here that's at position 0, and we move it to the left by 3, where's it going to end up at? This bit right here at position 0, if we move it to the left by 3, it's going to end up at position 3. So this 0 moves over to here. If we take this 1 at position 1, and we move it to the left by 3, where's it end up at? 4. So we're going to end up with the 1 here. This guy, if we shifted him to the left by 3, where would he end up at? 7. But do we have a spot 7 to put him? No, so he gets thrown away. This 3, if we move him to the left by 3, he would end up at 6. But do we have a spot 6? No, so he gets thrown away. The 2, if we moved him 3 to the left, he would end up at position 5. Right? So he'd get thrown away because we don't have position 5. Now we have these 3 blank spots, and so we bring in zeros to fill them in. So 0, 0, 0. Does that make sense? Does anybody want to see another example? With right shift, the bits move in the opposite direction. So let's say we were doing a logical right shift by 2, right? If we shift this guy to the right by 2, where does he end up at? Negative 2. Do we have a spot for that? No. If we shifted him to the right by 2, he'd end up at negative 1, and we don't have a negative 1 spot, so he gets thrown away. We take this 0, and we move him to the right by 2. He's going to end up at position 0, so he moved over to 0. This 3, if we move him to the right by 2, ends up at position 1, so that 0 goes there. And then finally, this 1 is at position 4. If we move him to the right by 2, he ends up at position 2, right? We'll just do subtraction to figure out the new spot. Now, if we're doing a logical right shift, what do we bring in? Zeros. So we'd end up with 0, 0. Now, let's say instead of doing a logical right shift, we had instead done an arithmetic right shift. What would we get? We would get 1s at both of these spots because the most significant bit is a 1, right? If you do an arithmetic right shift, you bring in the most significant bit. But now let's say that this bit over here had been a 0. Well, this guy needs to change to a 0. But what bits would we shift in here if we were doing, maybe we'll make this a little bit more interesting, turn this to a 1. So he ends up here. Now if we did an arithmetic right shift, what would we bring in here? Just zeros, right? Because again, the most significant bit is 0. Any questions on the shifting? Yeah. There is no logical left shift. I mean, or you can say the logical left shift and the arithmetic left shift, they are equivalent to each other, right? So you always bring in zeros at the end. Yeah. So we're not talking about how numbers are represented yet, but we will get into the point about how signed numbers and unsigned numbers are represented in a minute. Any other questions? So let's talk about what you can use each of these operators for. So a bitwise AND, it can be used for 2 different things. It can be used to check if a bit is a 0 or 1. And it can also be used to check if a bit, or to change the values of a bit to 0. So you guys may have heard this before, but let me just double check. Do you guys know what is considered to be false in programming? What's false? 0. So if the value is 0, it's considered to be false. What's considered to be true? Not 0. Not 0 is true. So if you evaluate some if expression, and if you say if 5, will we go inside the if statement? I mean, it seems like a stupid thing to write, but if you did write if 5, would that if statement be executed? Yes, because it's not 0. So watch out for that mistake. So to check to see if I guess we should also back up a little bit here. What's A or 0? It's A. A or 1 is 1. A and 0 is 0. A and 1 is A. A XOR 0 is A. A XOR 1 is it's not A. It's the opposite, right? Because if A is 0, 0 XOR 1 is 1. But if A was 1, 1 XOR 1 is 0, right? So you end up with the opposite of what you have. So notice what we can kind of do with each of these operators. We can use the OR operator to change bits to 1. If you want to change a specific bit to 1, what would you put at that spot? If you wanted to change a bit to a 1, you can use the OR operator, right? So let's show that happening. Oops. So let's say that I wanted to change bits 2 and 4 to 1. What operator would I do? What operator would I use? We would use OR, because if we look at OR, we can force things to become 1. So if I want to change bits 2 and 4 to a 1, I would put a 1 here, a 1 here. Let me just do one thing. Right, so our operator will be an OR. We can put 1s here, and what should we put in the other spots? 0. And if I OR this all together, it's not there. If I OR this all together, this spot's going to end up being A or 0 is A. So this spot's going to end up with A5. A4 is going to end up being 1. A3 is going to end up being 3, 1, A1, A0. Right? So if you want to change bits to be 1, right, you OR it with 1s at the positions that you want to become 1 and 0s in every single other spot. Does this make sense so far? Right? If we did have this variable A over here and I wanted to write this in C code, I would do something like A or equals, because I want to change A, right? If you want to write binary, it's 0B, and I want 0, 1, 0, 1, 0, 0. And that would change those bits of A over to be 1. Bits 2 and 4. Any questions here? What happens if we wanted to just be able to change bit I to 1? Is there any generalized statement that we can make? Yeah?
No, never mind. I thought I had an idea, but I didn't.
Okay. So what happens if we just started out with 1 here? Right? This 1's at position 0. Agreed? Right? But we want to get our 1 to what position? I. So how can I move my 1 to position I? Left shift it by I, right? Because if I wanted to get to position 3, I want to move that 1 3 to the left. If I want to get to position 5, move it 5 to the left. Position 4, 4 to the left. So down here, I would do A or equals what do we want to move to the left? 1. And we want to move it to the left? I. Does that make sense? Right? Because if we take this bit and we move it to the left, say by 2, that 1 moves from here, and then we have to fill this in with 0. So now I have a 1 at position 2, and that's just going to make a 1 be at that spot. Any questions here? There'll be zeros there because we originally started out with 1, right? And so if we move these bits, say 2 to the left, right, there's going to be zeros over here, right? There's all zeros in front of it. So the only space that's going to end up being non-zero is the spot that we move it to. So if I want to move it to position 2, right, this 1 moves 2 to the left. The 1 ends up here. And then we get zeros to fill in for the bottom. And we had zeros before it, so there'll be zeros in front of it still. Any other questions here? Yeah. Correct. Shift and then OR, right? Because I have to compute this expression first, and then I'll do the OR equals. I mean, this changes this expression right here as written is the C code that you would write, or C++ code that you would write to change bit I to a 1. What happens if we want to change bits I and J of A to 1? What expression could we write here? If we want, so yeah, you want to do it twice. You want to do A or equals 1 shifted to the left by I, and then A or equals 1 shifted to the left by J? Yes, this will work. Can we do it in a single line though? Yeah, you can OR them together, right? So we could take 1 shifted to the left by I, and then OR that with 1 shifted to the left by J. Right? Because if you think about what happens in the ORing, if we insert an extra line here, right? If I wanted to, oops, not there, here. If I want to get a 1 in position 2, right? I took 1 and I shifted it to the left to be at 2. If I want to also change bit 4, I would take my 1 from here and move it to the left by 4, right? So we'd end up with a 0 here, a 0 here, 0 here, and 0 here. If I then OR those two things together, right? If I OR these two lines here together, what do I get? Well, I get 0, 1, 0, 1, 0, 0, right? Which is what we had at the beginning. And this is going to change both bits 2 and 4 when we finally OR it with A. Does this make sense? Yeah.
Why does the 1 in position 4 not also get shifted to the left if you're shifting the whole?
No, because again, we started with 1, right, at position 1. So it started here as being at position 1, and now move it to the left 4. 1, 2, 3, 4. The 1 moves here, and we get zeros to fill in those spots. So this guy right here, this is 1 shifted to the left by 2. This is 1 shifted to the left by 4. This is 1 shifted to the left by 2, ORed with 1 shifted to the left by 4, or these two lines together, and then finally OR the result with the A at the beginning.
Yeah, like if you shift 1 to the left by 2 and then 1 to the left by 4, is that shifting the bit to the left by 6?
No, because again, we're shifting two separate things, right? Right? If you multiply A by 5 and multiply B by 2, right? It's not changing the original, right? The reason A changes is because it's being assigned here, or equals, right? This just computes some new value. Or if I just did something like this, like A or 1 shifted to the left by I, would this change A? No, right? Because A is equal to something. Just like if you did A plus B. It doesn't change A, it doesn't change B. You got to say it's equal to something if you want to change in value. Does that make sense? So let's say if we want to change bits to 0, right? If we back up to this table up here, which operator looks like it would be useful for changing bits to 0? And, right? Because and's the only one where you end up with 0 at the end, right? So in spots where we want our bits to change to 0, what should we put there? The bits that we want to change to 0, when we AND them with our new value, what should we put at that spot? Should we put a 0 there or a 1 there if we want that bit to change to a 0?
0.
0. If we want to leave it alone, we put 1, right? Because again, if we want it to change to a 0, we got to put a 0 there to make it happen. If we want it to stay the same, we put a 1 there and it won't change. So let's say we switch our operator over to be doing an AND now. And let's say that, again, we want to change bits 2 and 4 of A to 0. What should we AND them with? Change bits 2 and 4 to 0. 0 here, 0 here, and everywhere else should be 1s. And so now when we do our ANDing here, right, we're going to get A5 comes through, but now we're going to have 0 for A at this spot. A3 comes through, A2 becomes 0, and then A1 and A0 both come through. Does that make sense? Right? So if I wanted to do this, it would be something like A, right, and equals 0B, 1, 0, 1, 0, 1, 1. That's an N. 0B. Assuming our number is only 5 bits big. Now, what happens if we want to be able to change bit I of A to 0? A and equals. What am I shifting? I mean, sure, I'll shift something to the left by I, but what am I shifting? That would move all of A's bits to the left by I, right? So let's say, what happens if we tried 0? So what's the representation for 0, though? 0 is all 0, 0, 0, 0, 0, 0. So if I move that to the left by 2, what am I going to end up with? 0, 0, 0, 0, 0, 0, 0. And then if I AND it, I'm going to end up with 0, right? So this won't work. This will just be the same thing as A is equal to 0, right? If you attempt to do this, you'll just get A equals 0 because this expression is always going to evaluate to be 0, and you'll end up with, when you AND something with 0, you get 0. Yeah?
So what is the original value of A?
Does it matter? Right? This bit right here is either 1 or a 0. This bit over here is 1 or a 0. This bit over here is 1 or a 0. Right? It's whatever bits happen to be there beforehand. Because a lot of times you're going to be working with something and you don't know what's there, but you know what you want to change and what you want to leave alone.
So after using and, we just assume some of them will create 1 and some of them will create 0.
But so we know from back here that if we do A and 1, we're going to get A, and A and 0 is going to be 0. So in these spots where we put 0 down here, right, we're going to force the result to be 0, right? But these spots where we ANDed it with 1 in the spot, it makes it stay the same. So you'll end up with whatever you had before. So if A3 was 1, you're going to get 1. If A3 was 0, you're going to get 0 in that spot. So what happens if instead of trying to shift 0, we had instead shifted 1? So again, let's say we're trying to set bit 2. Well, this would put a 1 at this spot right here and zeros everywhere else. If we then did our AND, what would we end up with? Right? If we ANDed A with this expression, which bits would come through? Only A2, right? And all the rest would be forced to 0. But we want A2 to be 0 and the rest to be what they were, right? So is this the pattern that we want? No, it's in reverse, right? So how can I reverse my pattern? We can negate it, right? We can use not to flip the pattern. So that's what we'd end up doing would be A and equals not 1 shifted to the left by I. Right? That'll put on our original, right? Our original value, we'll put a 1 here, but then we'll flip, so we'll get 1, 1, 1, 0, 1, 1. And then if we ANDed our expression, our original A with this expression, right, A2 becomes 0, and the rest get left alone. Does that make sense? Yeah.
So how do we get the second line if that's 0, 0, 0, 1, 0?
This line right here. This, again, because we're trying to change bit 2 in this example, this is 1 shifted to the left by 2, which is our I.
So where would you like to shift to the 2 on the page?
So again, we're saying that I, right, in our example, I is equal to 2.
Okay.
So when we shift 1 to the left by I, it's going to move it to the left by 2. Mm-hmm.
So what does it evaluate to? Is that like 3 bit string or 6 bit string?
It'll be a 6-bit string at the end. In general, though, it depends on the size of your variable. So if we're working with integers here and A was an integer, we'd actually have 32 bits. If we're working with a short, it would be 16 bits. If we're working with a single character, it would be 8 bits.
So the other bits are like assumed to be 0?
So yeah, if you don't specify a bit, it's assumed to be 0, right, leading. Right, which is why doing something like this is a little bit dangerous. Because again, if we were working with an integer, right, and we really only wanted to change bits 2 and 4 to 0, this would be wrong, right? Because we've said 0, 0, 0, 0, 0, 0, 0, 0 all the way in front to make up 32, right? This would only affect the lower 6 bits, but we'd want to leave the remaining ones what they were supposed to actually be, right? But this answer over here would work correctly for changing bit 2, right? Because it's going to make sure all the bits but bit 2 are 1, and only bit 2 is 0. So this guy right here is much, much safer to be using, and what you should be using. Mm-hmm.
Even shifting this space to the left, make it 0, 0, 0, 0, 1, 1, 0, 0?
So what am I shifting? Am I shifting A?
Yes.
No, I'm shifting 1.
With bit 2 is 0.
Oh, I see.
Right, I'm shifting the 1, right? What if bit 2 was already 0?
Yeah.
Well, how did you know it was 0? Right? I mean, if you already knew it was 0, yes, you could skip doing this because it's already 0. But if you don't know what it is and you want to make sure that it ends up being 0 after the operation, this is what you would do. Right? What happens if we wanted to change, oops, caps lock, change bits I and j of a to 0? Again, we're still going to do a and equals, but a and equals what?
Not 1.
Not, oops, not 1 what?
Not 1 shifts to the left by I.
So like this,
And
or that with,
not 1 shifts to the left by J.
yeah, not 1 shifted to the left by j. Totally work. Or as an alternative, another way of doing it, you could say a and equals the negation, right, of 1 shifted to the left by I, or with 1 shifted to the left by j. Right, both will give you the same effect. Right, you basically like put the 1s in the spots that I want, and then flip them to 0, is what the second one's saying, to make sure that 0s end up there. Everyone cool so far about changing bits to 1s and 0s? So now let's see if I wanted to check if a bit is a 1 or a 0, right? Which operators up here look like they might be helpful for checking to see if a bit is a 1 or a 0? And seems like it's going to be useful, right? Because if we want that bit to pass through, right, to be able to check it, what should we put in that spot? A 1, right? Because we want it to come through. If we don't want it to come through, we put a 0, right? So let's say we're over here now. And let's say we want to check if bit 3 is a 1 or a 0. Right? So we would put a 1 at position 3, and we would put 0s everywhere else. Right? When we do this and, we're going to end up with A3 here, and what everywhere else? 0s. Because we ended them with 0s. So how will I know if A3 is a 1 or a 0? Because again, now the only bit that we have coming through right now, right, is A3. Okay, so we did do an AND, right? We ANDed it with this bit pattern. These other bit patterns, the secondary bit patterns we've been working with, they're kind of referred to as masks because they can either be used to mask off a variable or to mask on a variable. Turn it on or off. Or again, just look at something. So again, we get A3 coming through here. Let's say if A3 was 0, what would our expression be? It would be all 0. And before we talked about what's considered to be true and what's considered to be false. So if it came through as being all 0s, would this be considered true or false? False, right? But if A3 was a 1, this expression down here, what would its value be? Not 0, so it would be considered to be true. So what you could do here is do something like if we wanted to check to see if bit 3 specifically was a 1 or a 0, we could say if A and 0B 1 0 0 0. it is a 1. Else, it is a 0. Does that make sense? Because again, if this value here, if A3 is 0, the expression will evaluate to be 0, which is considered to be false, and we'll enter the else statement. We won't enter the if statement. But if A3 is 1, the expression will not be 0, so it'll be considered to be true, and we will go into the if statement. And yeah, it's a 1. And you can do something based on whether it's a 1 or not. Yeah?
The position of A3 in this example is not very important.
Well, I mean, like, A3 is important because we know which bit we want to check, so we know what bit pattern to write. Right? If the bit pattern was, say, bit 1, my bit pattern would have to change to be that. Right? So the bit pattern matters to check the correct bit.
You don't need the trailing zeros in the back.
Well, again, if we don't specify the leading values, they default to 0. So I don't need to specify them here. The one where you kind of need to be careful about is accidentally changing bits to 0 you didn't intend to with AND. So let's say we wanted to be able to generalize, and we want to be able to check if bit I is a 1 or a 0. From going from this expression always checks what bit? The bit at index 3, right? Now we want to be able to generalize to be able to do the bit at index I. So which part of this expression needs to change? If instead of checking 3, we want to be able to check bit I. The thing after the ampersand, right? The bit pattern. So we know it's going to be something very similar to what we have here. But we know that this part right here needs to change. And how have we been doing bit I this entire time? Not and equals changes, right? But we don't want to do an and equals. We don't want to change A. Right? But how have we been doing bit I every single time up until here, right? Bit I, right? Bit I, bit I. How have we always specified bit I? One shifted to the left by I, right? So again, you're just combining what we've just talked about together to change bit I to be 1 shifted to the left by I. And you notice I keep doing parentheses around these shifts. It's because of order of operations. The shifts have lower precedence than the ands and the ors. But I want to do the shift first. Otherwise, if I left off the parentheses, I would and A with 1, and then I would shift A to the right or to the left by I. So let's let you check bit I. So you can do homework 2 now. Homework 1.2, the alphabet question. Yeah. So if you want to check bit I, right, we need to have a 1 in I spot and what everywhere else? Zeros, right? So again, if I want to check bit 3, right, I'm going to start with 1. Oops, 1. Over here. Let's say I now move this bit pattern, right, because this is 1. This is just, 1. If I move 1 to the left by 3, what do I get? 0, 0, 1, 0, 0, 0. Hey, look, that's the pattern that we had before. Right, when we want to check bit 3. So if we want to check bit 3, right, we take 1 and we move it to the left by I, in this case 3, and then we can AND it again with the original, and you'll end up with just A3 coming through. And again, if A3 is 0, the entire expression will be 0, and 0 is considered to be false. If A3 is not 0, it's 1, this expression will be non-zero, so it'll be considered to be true. Yeah.
Like I'm confused what makes something true if it's just like 0, 0, 1, 0, 0.
So if there's at least one 1 in the bit pattern, it's considered to be true, right? Because at that point it's not 0.
So any length of zeros is just false, and then once you put ones in there, it would run with a statement.
Yeah, we're going to talk about like numbers in a couple of minutes, I guess, and see how they're represented. But like the bit representation for 0 is 0, 0, 0, 0, 0, 0, 0, 0, 0. It's all zeros, right? And everything else has at least one 1 in it. So that's why all the other values are considered to be true. Yeah.
So, for example, we assume that we know that we check the number 3 part.
Yeah, we're right, because generally, like if you want to check bit I, you kind of know what I is, right? Or again, if I was a parameter and the user wants to be able to check bit I, this expression is going to work, right? If the user wanted to check bit 3, I becomes 3. If the user wants to check bit 7, I becomes 7. The user wants to check bit 2, I is 2, right? This allows you to check any bit where I is the bit you want to check. Now finally, what would happen if in our check we ANDed it with something that had multiple 1s in it? What would you be able to say? Right, if we had a 1 here and a 1 here, right, this would give us a 1 here. So if both A3 and A1 are 0, you know that this expression will evaluate to be 0. And so you would know that both bits are 0, right? But if A3 was 1, right, you'd enter the if statement. If A1 was 1, you would enter the if statement. So you end up entering the if statement when? When either one of them is true, right? Or at least one of them is true, right? So if you're doing some check like this, you're ending it with 1s in multiple spots, you're like, I want to see if any one of these bits is 1, but you don't necessarily care which one is. Which one is 1. If you want to be specifically check bit A3 or specifically check bit A1, you have to do them separately. Check bit A3, then check bit A1. No way around that. So, or the exclusive OR. What do you think exclusive OR can be used to do? Mm-hmm.
When like compare line of difference, get one.
Yes, you could use exclusive OR to check if things are the same, right? But you might also just use equal equal, right? Give you the same effect. Yeah, so XOR can be used to flip bits in your bit string, right? If you want the bit to stay the same, what should you put there? 0. If you want the bit to flip, put a 1. So every bit you want to flip, put 1s. Every bit you want to leave alone, put 0s. It's really uncommon to just want to flip bits, but if for whatever reason you just want to toggle it and make it the opposite of what it was, XOR it with 1s in the spot that you want to change. And the logic for being able to flip bit I, what do you think it's going to be? Right? Instead of doing and or we're going to use XOR, right? Right? If we wanted to flip bit I, what would the expression be of A? A XOR equals, don't get it confused with exponentiation, it's totally not. XOR equals, yeah. And if you wanted to flip multiple bits, flip bits I and J of A. Yep. That'll flip bits I and j. So right, so again, this is just saying put the ones at the spots where you want to flip the things. That's simple. So sometimes you might find you might have a single variable where you've packed multiple fields into it, and you need to be able to extract each of the individual fields. The procedure here is fairly simple, and you'll see some examples in the next slide. So we'll shift the variable containing the field to the right so that its least significant bit of the field ends up at index 0, and then AND it with a mask that has as many ones as there are bits in that field. So here's our example. Let's say we had an unsigned int. Its name is packed. And inside packed, we put 5 other numbers, right? We would only do this if we were really, really hurting for space, and the numbers that we had to represent were small. So I put 5 separate numbers inside of my variable, A, B, C, D, and E. Bits 0 through 6 are E, bits 7 through 5 are 7 through 15 are D, 16 through 17 are C, 18 through 29 are B, and 30 through 31 are going to be A. And the bottom tells you how many bits are actually there. So the way that we can make this work is we need to move, well, maybe I'll give you a smaller example to help you visualize. Probably a good idea. So here are our fields A, B, B, C, C, C. And we'll insert a row above, and here are their indices, 7, 6, 5, 4, 3, 2, 1, 0. Let's say I wanted to get field C out of here, right? So how could I get field C out of this spot? What bitwise operators could I do so that I'm only left with C? Do I want A? No, how can I get rid of A? And it was 0, right? Oops, too many. But I do want to keep C, so what should I end it with? 1, 1, 1, right? So after I do this, insert row below, insert column left. Right, we're doing the AND. After I do this AND, 0, 0, 0, 0, 0, C, C, C. So I left with just C. So C is going to be equal to, if this whole thing is just called num, C would be equal to num ANDed with 0b, or just 1, 1, 1. Right? Because the preceding bits are assumed to be 0, and it's annoying to have to type out 4 extra zeros if you don't have to. Now, how can I get B? What would I want to AND it with? Right? So we could do 0, 0, 0, 1, 1, 0, 0, 0. And if I do this, I'm going to be left with BB here and zeros in these spots now. So after I get through, I'm going to end up with BB 0, 0, 0, right? Let's say B was originally, this guy was 1 and this guy was 0, right? So B originally is 1, 0, right? When I get this value out now, I'm going to have 1, 0, 0, 0, 0, right? Is that what I want? No, what do I want? I want just 1, 0, so how can I get that? Right shift, right? Because if we push things to the right, we're going to move it over to be the spot that we wanted at. So how much do I need to move it to the right by? 3 spaces, right, to get rid of the C. So I like to do it in the other way around, so I like to take num and shift it to the right by 3, and then we can AND it with, if we shift it to the right, first, we're going to end up with, if we move everything to the right by 3, right, we're going to end up with 0, 0, 0, A, B, B, right? This would be a right shift by 3. And then we're going to need to AND it with, well, what do I have to AND it with? I want, what here? 0, 0, 0. Do I want the A's? No. And do I want the B's? Yes. So this will give us 0, 0 now. And then after the AND, we end up with B, B, which is what we want. So we move it to the right by 3, and we AND it with 1, 1. If we want to get C, what should we do? No, not C. If we want to get A, what should we do? Shift num by 5, and then AND it with 1, 1, 1, right? 0, B, 1, 1, 1. Because if we right shift by 5, we're going to end up with A here, 0, 0. And then we need to keep our bottom 3 most bits, 1, 1. And now we're going to end up with A. So what's the general rule of thumb? How much do I need to move something to the right by? Right, because we need to generalize to be able to pick out any field, right? Why did I need to shift B to the right by 2, right by 3? Because the last B is in the 3rd spot, and we want it to end up at what spot? 0, right? So we look at the lowest bit in the field, right, and we right shift it so it ends up at spot 0, right? Then we had to AND it by how many 1s? Yeah, how many B's we had. How big's the field? It's too big, so we had to AND it with 2 1s. Or if we look over here when we tried to get A, A's lowest bit is at position 5, so we had to right shift it by 5. How many bits are in A? 3. How many bits did we have to AND it with? How many 1s did we have to AND it with? 3, right? C, how much did we have to shift it to the right by? 0. So, if we want to kind of like make the pattern, move it to the right by 0, doesn't change, and then we ANDed it with 3 1s because there are 3 C's. Is this making sense? So if we go back to our slightly larger example, if we're trying to get A, how far to the right do we have to move A by? Where's its lowest bit at? It's at 30, so we have to shift it to the right by 30. How many 1s are there? Or how many bits in the field are there? 2, so we had to AND it with 2 1s. For B, how far to the right do we need to move it? 18, because its lowest bit is at position 18. Then how many 1s do we have to AND it with? 12, because there are 12 bits in the field. C, how far to the right do we need to move it? 16, because its lowest bit is at 16. Then how many 1s do we have to AND it with? 2, because there are 2 bits in the field. D needs to be moved to the right by 7, because its lowest bit is at 7. And then we AND it with 9 1s, because there are 9 bits here. E, we move it to the right by 0, right? Because its lowest bit is at position 0. And then we AND it with 7 1s, because we need 7 1s. There's 7 bits in the field. Does that make sense? And you can kind of do the inverse of this if you actually needed to pack the number together. Like you had the separate fields, and you wanted to shove them into one variable, you do the inverses with ORs and left shifts to put them in the spot you want to be at. Any questions here? So you may ask, where does this actually end up happening? So you guys may or may not be aware, but every file in your system has permission bits. Read, write, and execute. They are 3 bits, 0, 1, 0, right? So you might need to be able to flip those bits or pull those bits out to figure out if you have read permission or write permission. So one final note, because I still got 3 minutes, is a bit pattern by itself has no particular meaning. If I give you some pattern, 1011, it can have different meanings in different contexts. A good example of this is 101. In our example previously, it meant cat. But it might also mean the number 5 or the number -3, or it could signify read and execute permissions on a file. But it depends on the context. A context from real life is something like the word write. What does write mean? It could be a lot of things, right? But if I say turn right here, what does right mean? You know, it's this direction over here, right? If I say you are right, it means you're correct. If I say write that down, right, inscribe it on your paper, you know what right means from the context, right? Or, you know, what about 9? What does 9 mean? It might mean no if we're speaking German, but, right, it might also mean, you know, 9 numbers after 0, right, if we're talking in English and we're talking about numbers. So again, context matters a lot, right? In a high-level language, this is normally figured out through types, right? If I have some bit pattern that's supposed to represent an integer, and then it represents -3, right? The int means that I want to consider it to be a signed number. But if I put that same bit pattern into an unsigned integer, it's going to be interpreted as 5, because I'm saying I want to interpret these bits as an unsigned number with having no signedness, positive or negative. At the machine level, we kind of figure this out based off of what instructions. If I'm like adding and stuff together, I'm probably meaning that this thing is going to be a number. If I'm checking to see like if this characters or if this bits are the null character, I'm probably treating them like characters and not numbers. So you can infer from the instructions as to what the type is. But again, it's an inference, and sometimes we kind of mix and match meanings together. So next week, we will talk about representing numbers, but you definitely know enough to do problem 1.2 now if you want to start, the alphabet problem. If you just read a little bit ahead up to this slide, you'll be able to do problem number 1. So that's the answer to problem number 1.
As for the homework 1.1, should we C++?
So the file needs to have a CPP extension, but C is a subset of C++. So if you write pure C code, it'll still work. But if you want to use C++ conventions to make your life easier, go ahead.
Okay.
Like why we use OR at that time.
For XORing.
Yeah.
So if I wanted to flip bits I and J,
Yeah.
right? We said earlier that if we want to flip a bit, we need to put a 1 at that spot.
Yes.
Right?
Yes.
So if over here are my bits 0, 1, 2, 3, 4, 5, right? If I want to flip bits 4 and 2,
Yeah.
I need 1s here at both these spots.
Yeah.
So let's say I take 1, right, and I shift it to the left by 4. That's going to be 1
Yeah.
here, right? If I take 1 and I shift it to the left by 2, that's going to end up with a 1
Yes.
here, right?
Okay.
If I OR both of these values together, I get 1s at both those spots, and then I can do the bitwise XOR to put the bits of my value that I'm interested in changing.
So, like
Someone dropped their idea. So
Oh,
hopefully you can,
thank you.
so for the operation, is that
Nope.
No. Okay. So for that
Use bits. Yeah.
operation, like we first do this and do the OR and last we do that.
XOR, right? Just for example, if you're doing this, a plus equals 3 plus 7, right, times 2, right? We'll do the times 2 first, get
Oh,
the 14, then add that 3 together to get 17, and then we'll add that into the A, right?
Okay.
This thing always happens at the very end.
Oh yeah. Thank you.
Professor, if I want to do the 1.3 ahead, what chapter should I do?
Problem 1.3, can you remind me? That's